All right, so when last I left you, we had been going over these phase diagrams, right? Different areas of the diagram represent solid, liquid, gas. If we do different things, temperature or pressure-wise, we can get a substance to change phases. So I left you with this parting question. Why is it that some electronics that are supposed to be waterproof can't go in the dishwasher? I've got a supposedly waterproof toothbrush. It says don't put it in the dishwasher. Same thing with your iPhone. Same thing with your iWatch. Why can we not put it in the dishwasher relative to what we're talking about here? Your dishwasher is a sealed box. We pump water into the dishwasher and then we heat it, right? There's a heating element in the bottom that is going to heat up that liquid. It's going to increase the temperature of that liquid until it becomes a gas. So we're talking about transitioning from a liquid to a gas. Well, we're going to continue to heat that. We're going to continue to increase the temperature of that system until we're going to start to vaporize some of that water. So now we've got a pressurized system where we've got our liquid water going into the gas phase. Now we're going to have a super dense gas. I can't guarantee you that it meets the criteria of a supercritical fluid, but we definitely have a dense gas under pressure and is going to be able to shove individual water molecules into the tiny little gaps around the seals in your electronics. They're going to get in there and they can cause damage to the inside. They can recondense once the temperature drops in your dishwasher, at which point, when it recondenses, it becomes liquid and it shorts things out. So it's a factor of phase changes, temperature, and pressure that is why these waterproof things are not dishwasher proof. All right, so the end of this chapter then, the conclusion is that there are differences between intermolecular forces. The differences between the intermolecular forces can be seen when we talk about evaporation, boiling points, things that have to do with a transition between one phase and another. Things that have higher intermolecular forces, you're going to have to put more energy into that substance to get it to change phases. We have been talking about those intermolecular forces that are most appropriate for us to think about when we're talking about those covalent compounds. What we haven't talked about is how that relates to ionic compounds. So in Gen Chem 1, when we're talking about ionic compounds versus molecular compounds or covalent compounds, we're saying that there's a difference in the melting points between these two compounds. Salts, ionic compounds, have very strong forces between the molecules because it's a repeating crystalline solid. It's sodium chloride, sodium chloride, sodium chloride. That's in 3 dimensions. So if you want to bust one of those sodiums out, you're going to have to disrupt attractive forces all the way around that sodium. Now when it comes to the molecular or the covalent compounds, there is no electrostatic, there is no positive-negative attraction between those molecules. What does it have? It could have hydrogen bonding, dipole-dipole interactions, it can have dispersion forces. All of those are weak attractions. So those are going to have melting points that are much lower. So in Gen Chem 1 we talk about, if you've ever watched one of those movies where they're dealing with narcotics or something and they want to know the purity of the stuff, what do? They put it in a spoon or something and they try to heat it up to see where it melts. Well, if somebody knows what the appropriate melting temperature is for that compound and you're trying to fool them because you put table salt in there or something that is an ionic solid, you're going to be in trouble, and for the rest of the movie they're probably going to be chasing you through the jungle, because that stuff's not going to melt in the same range as covalent compounds like those narcotics. So what does that look like? We talked about for the ionic compounds, it's this repeating pattern over and over and over again in 3-dimensional space. So you're not just trying to get one side of an interaction, you're trying to disrupt 360 degrees of interactions for every one of these ions. Examples like sodium chloride, aluminum oxide, things we learned about in Gen Chem 1 to be ionic compounds. They fit into this tight crystalline solid. You don't get to meet ionic compounds that aren't crystalline solids at room temperature. When it comes to covalent compounds, things like water, liquid at room temperature. Carbon dioxide, gas at room temperature. They have weaker intermolecular forces, so they're not locked into the solid state. They're not locked into a crystalline solid. And when they do form a solid, it's a weak or brittle solid. So if you think about what one of those solids would look like, you can have solid iodine at room temperature. It's a solid. It's not a crystalline solid because it doesn't have that same repeating pattern. There's space. Look, we got some space in there, some space in there, some space in there, space in there. So when you put pressure on it, it's going to crumble. It's brittle. You bite into a salt crystal, it crunches, right? That's going to be more of that crystalline repeating solid. So ionic solids, composed of ions, ionic bonds, high melting points, high to very high melting points. These molecular or covalent solids made up of molecules, strongest that you're going to have intermolecular forces, lower melting points, because intermolecular forces are weak. So that's all we want to say about the rest of Chapter 10. So now we can move on into Chapter 11.